Okay, here's an example of an integral of a rational function, which we can tackle with partial fraction decomposition. So let's take this and rewrite it as something that is equivalent with the denominator, or sorry, with the rational function decomposed. So we can write this as ax plus b over x squared plus 4. Remember, x squared plus 4 is an irreducible quadratic polynomial, so we'll want to write it like that. There's no way to simplify that more without using complex numbers. And then plus c over x plus 1 dx. So this is how we want to transform this integral. So now let's forget that the integrals are there and just focus on the equivalence of the functions inside the integral. So we'll take both sides of this equation and we'll multiply by the denominator on the left-hand side. And so that will give us 3x squared plus 3x plus 10 on the left-hand side. And then it'll give us ax plus b times x plus 1 plus c times x squared plus 4. Okay, so now we have an equation involving a, b, and c, but it's a polynomial equation, so we'll be able to turn it into 3 equations, but we have to do a little bit of work first. So I'll switch the left and the right hand sides of this equation and simplify it a little bit. So if I FOIL this out, this ax plus b times x plus 1, I'll get a x squared, and then my x terms will be bx plus ax, so that's plus a plus bx, and then plus b. So there we go. And then finally we have plus cx squared plus 4c multiplying out that last term. So we have this entire thing is equal to the left-hand side in the previous step, which we're changing to the right-hand side. So there we have 3x squared plus 3x plus 10. Great. And like I said before, this is a single polynomial equation which we can turn into 3 equations for the coefficients a, b, and c. So what we'll do is we'll look at the coefficient of x squared on both sides of the equation, the coefficient of x on both sides of the equation, and the constant term on both sides of the equation, which I'll denote by 1. So on the left-hand side of the equation, the coefficient of x squared is a plus c, and then on the right-hand side it is 3. Good. And then the coefficient of x on the left-hand side of the equation is a plus b, and then on the right-hand side it is 3. And then finally, the constant term on the left-hand side of the equation is b plus 4c. Good. And then on the right-hand side of the equation, it's 10. Good. So our next goal is to solve this system of equations. So I'll clean up the board, and then we'll solve this system of equations. Okay. So now we're ready to solve the system of equations. So there's lots of ways to solve a system of equations like this. I'll use the substitution method, even though it's not the quickest way to do it. The quickest way would maybe to be use an augmented matrix, but that's usually in a linear algebra course. So let's see what we can do with these first 2 equations. As you can see, these are easily solvable for c and b in terms of a. So here we can write c equals negative a plus 3, and b is also equal to negative a plus 3. Good. Then next, what does that tell us? So we can plug c and b into this second equation. So we have negative a plus b, sorry, plus 3, plus 4 times negative a plus 3 equals 10. So now we've gotten down to 1 equation and 1 unknown. So a is our unknown. So we have negative a minus another 4a, so that gives us negative 5a. And then we have 3 plus 4 times 3, so that'll be 3 plus 12, so that's plus 15 equals 10. Good. So that gives us negative 5a equals negative 5, or a equals 1. And now that we've got this value for a, we can use it along with the top two equations on the right up there to get values for b and c. It's easy to see that b and c will have the same value. So let's see what we get. So we'll have b equals negative 1 plus 3, so that's 2. And then similarly, c is also 2. Good. So now we've solved for our unknown coefficients and we're ready for the next step. So I'll clean up the board again and then we'll finish this problem off. Okay, good. So now we're all set to finish this problem off. So let's recall what we started with. We started with an integral of a rational function. We argued that we could decompose this rational function as follows with unknown coefficients a, b, and c. That gave us a system of equations that we could solve for a, b, and c, which we did, and I've put over there. So now let's substitute those into this equation. So that gives us x plus 2 over x squared plus 4 plus 2 over x plus 1. So this is the integral that we want to evaluate. So let's see what we can do there. Well, x squared plus 4 in the denominator here, if there's a constant in the numerator, we know that it's an inverse tangent type antiderivative, and if there's an x in the numerator, we know that it's like a natural log type antiderivative. So we actually need to split this term into two. So let's do that. So here we get, this is the integral of x over x squared plus 4 plus 2 over x squared plus 4 plus 2 over x plus 1 dx. Okay, so let's see what we can do from there. So this will be inverse tangent, this will be a natural log, and then here maybe we need to do a little bit of a u substitution to see what we get. So if we let u equal the denominator, x squared plus 4, that makes du equal to 2x dx. So that means we have u here in the denominator, and then this is really 1/2 du. So that allows us to split this integral as follows. So we have 1/2 the integral of du over u, where that's that substitution over there. And now let's go ahead and integrate these last two parts. So if you recall, the antiderivative of x squared plus 1 is the inverse tangent of x. So if there's a 4 there, there's something a little bit different to do. First of all, the 2 gets gobbled up, and then we've got something composed inside the inverse tangent of x. So I won't work out all the details, but here we get, this is plus the arctan of x over 2. Good. And then finally, this will be plus the natural log of the absolute value of x plus 1 plus a constant. So now we're almost done. So we can take the antiderivative of this, which will be the natural log of u, substitute u back in, and get our final answer. So this will be 1/2 the natural log of x squared plus 4 plus arctan of x over 2 plus the natural log of the absolute value of x plus 1 plus a constant. And that's our final answer.